Okay. So the first thing I want you to just correct on this is the quiz will be on Tuesday. We don't need Wednesday. We can do it on Tuesday. Finish going over the pre-calc topics. Remember the outline for this quiz is in the back of today's notes. It tells you what's going to be on it exactly. The very last page when you flip it over. So we'll finish going over the topics that are going to be on it, and then we should be fine. Okay, so you got your unit circle, and any problems lately in the quadrantal angles? We're right with this because I wanted you to do it in radians. See how you did here. So you should have for the angle 0, pi over 2, pi, 3/2 pi, and 2 pi. And then you want to label the points correctly. And just by doing that, right, this allows us, this is one way we can memorize the trig values of all the quadrantal angles. So if I were to ask you guys, ready, what's the sine of pi over 2? What would you say? 1. Thinking 1? Yeah. Remember, the sine is the y-coordinate. So if you know the coordinate of the point, you know the cosine and the sine. How about the cosine of 3 pi over 2? 0. If you're not getting this, please tell me. I'm just not getting, I can just explain it. So the x is the cosine of that angle, and the y-coordinate is the sine of that angle. Just try one more. How about the cosine of 2 pi? 1. Pi is over here. Okay, cosine is the x. 1. Just for fun, I want to see how good you are without looking at your notes. Let's just label the 3 special angles. In radians, 30 degrees is the same as pi over 6. How about 45? And how about 60? Now let's see if we know the coordinates of these points. And as we move from 0 radians to pi over 2 radians, what happens with the cosine? The x they decrease, and the y-coordinate sine increase. Okay, that'll help us get this right. Okay, pi over 6. What are the coordinates for that? What about when we get to pi over 4? And then pi over 3? Beautiful. So you can do that, and you see how the x's decrease and the y's increase. You do have the sine and the cosine, and the ability to just make sure we got this. What is the cosine of pi over 3? Cosine of pi over 3. 1/2. All right, we're just making sure we get how this whole thing works. Good times? Okay, good. I would still go through the flashcards, make sure you know them. Because on that quiz on Tuesday, I think I asked you like 18 of them or something. That's crazy. I'm sticking in the first quadrant for the special angles. I'm not taking it out. I'm putting it in the other quadrants. But yeah, any quadrantal angles. So, you want no calculator? You just want to take one with your calculator. You ever do that with edit? No. No? Okay, good. Glad you don't cheat like that. Okay, so we did that. I think we got to yesterday's note as far as we did the unit circle. The only thing maybe we didn't touch on was, and I didn't have it on your notes, like what secant is and cosecant and cotan. We did that? You guys saw. All right, good. So let's get to today's transformations. I just want to remind you what each of these numbers do. So let's say you have a function that you're really familiar with, like the absolute value of x, or square root of x. By the way, what does square root of x look like? Show me with your hands. No, wrong one. There you go, like that. How about absolute value of x? Ready? How about x cubed? basic ones. But now someone's gone and thrown some constants in. They either multiplied by a number outside or inside the function, or they added some number inside or outside. That's going to cause the graph to change. It's going to transform the graph, and in very frequent ways. Each one of these numbers will create a special effect, and you just want to know what each one does. So briefly, because I know you guys did this, and this is not on the quiz, that's why I'm going to go a little further. I just want to make sure you guys know this. Numbers that are thrown in outside, they cause vertical changes or horizontal changes. Vertical, right? What about the inside numbers? Horizontal. The other thing you want to remember, multipliers. Stretch your strength relations. Yes. And then numbers that are added with differentiation, they call shifts. So we've got vertical dilation, horizontal dilation, that's like the big thing. And then it's those horizontal ones that are always a little screwy. I mean, as far as A goes, it's going to cause a vertical dilation, stretch or shrink by the absolute value of A. So if there's a 2 or a negative 2 up front, it's going to cause a vertical stretch by 2. It's going to double all the y coordinates. If the multipliers are negative, they also cause reflection. So if A is negative, you reflect the graph about the x-axis. B is another multiplier, so it causes a dilation, but it's absolute value of 1 over B. So if you see a 2x inside instead of an x, it's going to take all the x's and halve them. It's going to be a shrink by a factor of a half. It's the outside, like if this is a 2 on the outside, you double the y, so it's going to be a stretch. But when it's an inside, it's the absolute value of 1 over b, so it would be a horizontal shrink by a half. Let me go to D first. D causes a vertical shift by whatever D is. If you see a plus 3, you move the graph up 3. If it's a minus 1, you move it down 1. That's nice. C is a little bit more complicated. It's horizontal things. The horizontal shift is always equal to negative C over B. So if you usually the B is 1. So if you see an x plus 2, the shift is going to be minus 2 over 1 or less 2. So I threw this here. It's really helpful when you're looking at equations just to have a sense of what the graph will look like. But again, I'm not going to quiz you, so I just wanted to go through that. We could do a little exercise with this. It's fun. Absolute value of x. You just sketch that in there. Y equals x. X is greater than or equal to 0. And y equals negative x when x is plus 0. So the absolute value of x, we know what that looks like. What is putting a 2 out front going to do to the earth? Yeah, it's going to stretch it vertically. It's going to double all the old y coordinates. So if you had some points on here that you use, you can keep the x coordinates and just double the y coordinates. So 0 with 0, it's going to stay 0, 0. If you double the y coordinates, it's 0. Well, like here I had the point 1, 1. What's this big one? Now when x is 1, what's y going to be? 1, 2. It's take the negative 1. Before I had the point 2, 2. Now the y is going to be doubled. So I'll have the point 2, 4. Since I'm just kind of held it, it's stretched it. Just doubled all the y coordinates. Like if I listed out every single the coordinates of every point on this graph, just kept the x's the same and doubled the y's, I'd have that graph. Y equals the absolute value of x plus 2. Because it's added, so we know it's a shift, but by how much and which way? 2 to the left. Now, I can do something that you can't. I do it here. I can. Oh, no! Wait, I can't do it. I'm just going to erase and do it again. Maybe because I did it in 2 pieces. I was trying to be really cool. See if I do it in one shot. Okay. over here. So it was over here. So then we just move it to the left. Oh, kind of. Actually, let's skip this one for a second. Let's do that absolute value of x plus 2. What if putting that plus 2 outside the absolute value going to do to the graph? Move it up 2. Clone it. Bring it over here. It was down here. Now it moves up. Now, the other one I have here, the multipliers inside. So it's going to cause a horizontal dilation, but by how much? Okay, that's the same, but it's a horizontal dilation by a factor of 1/2. So one way to do it, if you had it is by hand, you could just halve all the x's. You just keep the y coordinates of your original points the same, and just halve the x's. And in this case, it's going to look just like that one, but you'll see in a second. But it's not always the case. So before, like I had the point 1, 1. Now if I have the x's, I'll have a half 1. I have like negative 1, 1, so negative a half 1. I'm just going to have all the x's. 0, 0 stays the same. If you have the 0, it's still 0. Before I had the point, oh, let's see, I had 2, 2. Now if I have the x, I have 1, 2. Have the x, 4. So it's just because this particular graph that it is going to look the same as the other one. Moving on. Odd and even time, right? Remember how to tell if a function is odd or even. Like negative x in for x, right? And if it equals f of x, so in other words, whether I plug in 3 or negative 3, I get the same y. If I plug in 1 or negative 1, I'm getting the same y. And if we do this, whatever that y is, whenever you plug in a number and its opposite, you get the same kind of y value here. We say that this kind of function is even. And it's going to be even functions are always symmetric about the y-axis. You've got the point 1, 3 and negative 1, 3. If you don't have any point, you plug it over the y-axis, you got a point on the graph. So the way you remember is, the first thing you have to always remember, you have to plug in negative x into the function. But just remember, when you plug in negative x into the function, if it's equal to the original, then the function is even. There we go with this. And now it's symmetric about the y-axis. What do you say y in French or Spanish? The letter y. Say it again. I can never say that even one time. Okay, it's e something, e blah blah blah, right? So it's e blah 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 axis, the y-axis. This is how I would remember though. If when you plug a negative x into x, it equals the original, that means the function is even, and it's symmetric about the e blah blah axis, right? Y in French. I know that. I don't know the Spanish name. I have a hard time saying that. I have to see it written down. I think maybe if I was now, if you have a function, when you plug in negative x for all the x's, you get the opposite of the original value of f of x. You get negative f of x. Opposite. Then we say that that function is odd. So if you plug in 1, you get positive 1. Then when you plug in negative 1, you have to get negative 1. If you plug in 2 and you get 7, you plug in negative 2, you get negative 7. And if that's true all the time, your graph's going to be symmetric. symmetric about the origin. Great the way that works out. So it's either it's equal, it's even, symmetric about the y-axis. And if it's the opposite of f of x, it's not a function, so it's symmetric about the origin. We'll do some real ones. I just wanted to refresh your memory. But one thing, if you're asked if it's odd or even, just replace the x with negative x and compare it to the original. That's what you're doing. I mean, chances are it's going to be neither. Our first example, we have f of x equals x cubed. We want to know if it's odd or even. So we want to see what happens if I plug in negative x in for the x equals 5. You just replace the x with a negative x, and you clean it out. So if you took negative x and you cube it, what do you get? Negative x cubed. Now, does that equal f of x? Equal the opposite of f of x? Or neither? The opposite is equal to negative f of x. So is this function even, odd, or neither? Odd. So therefore, we hold that. Therefore, our function is odd. And once we know it's odd, we know about the symmetry. What's going to be symmetric about the origin. Not just the right origin. And you know that's true, because you know the graph of y equals x cubed looks like this. Alright, let's see our next one. So we want to know if f of x equals x squared is not or an even function. What's the first thing we have to do? Plug in negative x. So we look at f of negative x. So we replace anywhere we see an x, we just replace it with a negative x. And we clean it up. If you have negative x and you square it, what do you get? X squared. That is x squared equals f of x, the opposite of f of x, or neither? Equal. So what kind of a function is this? Even. Therefore, even function. So what kind of symmetry does it have to have, this graph? Y-axis. You know it does, right? Because you know y equals x squared. Like, it's definitely symmetric about the y-axis. Even function. And you see where the names odd and even come from. Look at our two examples here. What do you think it's called? Odd and even. So x cubed was odd and x squared was even. Yes, that's right. Yeah, it's that exponent. But you have to, if it's just x to a power, yeah, you can just go right off that exponent to see if it's odd or even. But once you start adding and subtracting different terms, be careful if there's a constant in there. But yeah, that's where the name comes from, because x to any odd power is going to be an odd function. Let's try another one. F of x equals x to the fifth minus 1. So, first step, we should replace the x with a negative x. See what it looks like. Okay, when you clean this up, what is it going to be? Right? 1. Now, does this equal f of x, the opposite of f of x, or neither? Neither. So, there is not going to be any symmetry about the origin or the y-axis, which is the right one here. Yes. Leave it blank. Yeah. Because what I'm going to say on the quiz is indicate any symmetry. So if you don't indicate any, that means there's none. Okay, well, these were all kind of fine and kind of familiar, right? But I want to look at sine and cosine. But what I'd like to do, I think would be more clear, I'd like to change it. Instead of calling it sine x, I'm going to call it sine theta. Just to, so if you don't mind, I'm going to just rename this. Instead of fx, it's the f of theta. C minus. I basically want to know if the sine function is odd or even. So always, first thing we do is we substitute in negative theta for theta. You just want to see what that's going to look like. You replace the theta with a negative theta on both sides. Then normally we clean it up. But sine of negative theta, that's a little bit tricky. It's not just an exponent. So that's why I want to go visit our old friend, the unit circle. He's back. I'm trying to see what is the connection. I'm trying to compare sine of negative theta to sine of theta. Like, is there any relationship between those two values? So sine of theta, this is theta here, would be which coordinate, x or y? Like, whatever this y coordinate is, that is the sine of theta. I mean, let's get a sense. What about sine of negative theta? Where would that be? Yeah, here. I would just go the other way, right? Like you went 30 degrees, negative 30. Same rotation is the opposite direction. And so I know the y coordinate here would be the sine of negative theta. Sine of negative theta. Now, the y coordinates of those 2 points. That's what I'm trying to say. Do you think that they're equal, opposite, or neither? Think about the y coordinate up there and the y coordinate down there. Do you think it's the same y coordinate? Opposite or? Yeah. You think they're equal? So I have 2 points. One here and one there. Y coordinate. That could be. No, y. Forget about the sign for now. The sign is the y coordinates. What do you think? It'd be the opposite, right? These y coordinates of those 2 points would just be the opposite. So we have to be a little tricky for this one to be able to compare it to the original. So it would be the opposite negative sine of theta. So what kind of a function is our sine? Therefore, sine is odd. Okay? And since it's odd, what kind of symmetry must it have? The origin. That's true. That's just a bunch of malarkey. Oh, let's think about what the sine graph looks like. Well, if I draw it beautifully, is the sine graph symmetric about the origin? Yeah, this works. This works. I got it. Okay, so we're going to approach the cosine. We're going to determine if cosine is odd or even the same way. I'm going to write in terms of theta, though. I'll keep the same picture up there. I can use that. But I just want to I want to use theta so it doesn't get confused with the x coordinate. I don't want to name the angle the same thing. So f of theta. So what do we do first to determine if it's odd or even? Plug in negative theta. So f of negative theta equals cosine of negative theta. But now I have to figure out a way to compare cosine of negative theta to cosine of theta. What's the x coordinate up here? Then equals theta. That's cosine of theta. And if we go the other way, theta degrees, so we're taking the cosine of negative theta, that would be the x coordinate down here. Just keep it away. Negative theta. Do you think that the cosine of theta, the x coordinate of this point up here, is the same, opposite, or neither? same. You guys all agree? I would say my coordinate. So it's equal. Cosine. So cosine is what type of function? Even. So therefore, cosine is an even function. What kind of symmetry does it have? About the y-axis. That part's just like automatic. Once you get the odd or even, the symmetry part is just automatic. If it's odd, it's origin. If it's even, it's y-axis. Okay. Question. Oh, and does it make sense cosine's even if we think about the graph? Is it symmetric about the y-axis? Yeah. Yeah, it all works. Okay. Next little pre-calc topic. Intercepts. X and y intercepts. If you want to find the x-intercept of the graph, where the point where a graph crosses the x-axis, it could be anywhere. But what's the one thing you know about that point? The y-coordinate has to be 0. So whenever you want to find the x-intercept, what do? Set y equal to 0 and solve for x. Set y equal to 0 and solve for x. So I have a parabola here, y equals x squared minus 9. I just want you to find the x-intercepts of that. Does anyone else want to give it a try? You've done that, done that. Well, I haven't talked too much to you. Okay, it's funny. So you, oh, very nice. So you plug that in and you factor to solve that. Oh, that's good. I like it. Uh-huh. So you have x equals 3 and x equals negative 3. Now, when you write your intercepts, write them as points so they don't look like lines. So points where our graph crosses the x-axis, negative 3, 0, and 3. Good. Because we already knew that y coordinate was 0. We could have filled that in right away. Just like the x. Okay, now, if you want to get the y-intercept, you're trying to figure out where this is going to cross the middle axis. What's the one thing you know about that point? Yes, that the x-coordinate's 0. So to find the y-intercept, what do? Set x equal to 0 and solve for y. That's a good idea. I like it. So using that same parabola, get the y-intercept. Just with your hand up, like ready to answer it. Oh, you were just like, okay. Well, I have to learn names. If I don't learn names, it's going to take me forever. Really bad. Okay, that's it. You want to try? Yeah, you do. Okay. You got negative 9. You put in, you have y equals 0 squared minus 9. So you got y equals negative 9. Now, when you write your answer, how do you write it as a point? 0 negative. Very nice. Beautiful. So now you're thinking, oh yeah, this is easy. I want to see what you guys get for this next one. So here's a graph. Oh, you can't see it on here. But I want you to find all the x-intercepts and all the y-intercepts. I'm not saying how many there are of each. But do your best with that one. Okay, so we have this little problem. So when you want to find x-intercepts, you put 0 in for y and solve for x. And we're going to solve this. We're lucky. It's a product. The only way two numbers can multiply together and give you 0 is if when either one of them is 0, right? So you set each factor equals to 0. I can easily do and solve each of these. Now, if x squared equals 0, what does x equal? 0. Right? You could take plus or minus the square root of 0. It's just going to be 0. So what about that other one? What do we do to both sides to get rid of that radical? So you don't have to, if that's what's bothering you, don't worry about it. The only way a square root of a number is going to be 0 is if the number 0. Now we solve for x here. What do we get? Plus or minus 3. So there are three x values that'll make y 0. So our x-intercepts are 0, 0, negative 3, 0, and 3, 0. The graph is going to cross all three points. What happens if when I'm looking for the y-intercept, I have to plug in 0 for the x's? We know x has to be 0 there. What do you get over there? 0. How many people said 3? I know a lot of people said 3, right? You said 3. Of course you did. Most people say 3 here because they forget about this, right? Because this is 0 times 3, but that's just 0. So we have 1 y-intercept. It's the point 0, 0. Beat yourself up. Yeah, I did that. I put it here for that reason. Now, this class ends like in a couple of minutes, but the last little part of the review has to do with equations of lines. And this is what you're going to have to finish up for homework. But I just want to make sure we're all good with point slope. Because the point, to write the equation of a line, if you think about, if you have a line, and there's some point, specific point on this line, x1, y1. So you have a point you know is on a line, and let's say we know the line has a slope of m. In order for another point to be on that line, so for any other point to be on that line, so for x1 to be on the point, we know that the difference of the y's, y minus y1, over the difference of the x's, x minus x1, has to equal m. Okay? For some other point xy to be on that line, difference of y's over difference of x's has to be the slope of that line, or it won't be on it. And if I cross multiply, we get the point slope form of an equation of a line. So, and this is so great. If you want to write the equation of a line, you fill in the coordinates of one point on the line, and you also have to fill in the slope. You leave the x and y alone. Okay? So we could do the bells in a ring, but we could do this first one. So for the first one, if the line has to go through the point 9, 10 and have a slope of negative 1/3, what's the equation of the line? Y minus 10, the y coordinate, equals negative 1/3 the slope times x minus 9. So y minus, and that is the equation of that line. So try to do the other ones. We'll go over it on Monday. Have a great weekend. After your first week.